Hello everyone, on today's video we will be doing another batch reactor example. Please feel free to pause the video at any moment if there's something you didn't understand, especially if you had a problem with the math and integral part of this course. I've made a video that's called Math Review Reactor Design, which will help you with the integrals and calculus part of this course. You can pause it, go watch that video, and come back. Let's go ahead and start with this example. Let's start by reading the problem statement. A liquid phase reaction A to B is to be carried out in a batch reactor. We identified the reactor we'll be working with a volume of 2 liters, constant volume of 2 liters. The reactor is assumed to be isothermal, basically meaning that the temperature will be constant and well mixed, with an initial concentration of 8 moles per liter of A. The rate of reaction is given by this equation here, where K1 and K2 are given. Calculate the residence time for the reactor required in hours to reach a final concentration of 2 moles per liter. So the question is asking you, what is the time required to reach a final concentration of 2 moles per liter? Unlike the first example we've done on a batch reactor, which was asking us what is the final concentration after a certain amount of time. So let's go ahead and write our givens. Volume is constant, which is 2 liters. Assumed to be isothermal, basically meaning that the temperature is constant, which means that the reaction rate constant. Since it's a function of temperature, that means it's also going to be constant. Well mixed basically means that at a certain amount of time, let's say the initial time times 0, the concentration anywhere in the reactor is the same, and at time, let's say the final time, the concentration anywhere in the reactor is the same. So that's basically what well mixed means. Okay, the initial concentration is 8 moles per liter. The final concentration is 2 moles per liter. The reaction rate equation is given by this equation here. K1 equals 6 per hour. K2 equals 3 per hour. Oops. The reaction rate equation looks scary, but really it's not. Since K1 and K2 are a function of temperature and the temperature is constant, we'll just be plugging these terms into the reaction rate equation. Okay, so we can go ahead and start with our material balance or mole balance. Okay, which is input minus output plus generation equals accumulation. Now these two terms are going to be 0 since there's no inlet stream or outlet stream in a batch reactor, so the input and output will be 0. We'll be left with generation equals accumulation. Generation, as we reviewed in the previous videos, generation equals rate of reaction times volume. And the accumulation is the change in moles over the change in time. Now we can sub in our rate of reaction, which is negative K1 Ca over 1 plus K2 Ca. The volume is constant, equals to. Now we need to change the differential in terms of Ca because that's the component we're working with, and we know that Ca equals moles over volume. Therefore, Na equals concentration times volume. Therefore, we can go ahead and sub this into the differential, which is Ca times V over dt. Now, since the volume is constant, it can go ahead and leave the differential. So we can take it out, and it'll look something like this. The volume will cancel on both sides. We'll be left with negative K1 Ca over 1 plus K2 Ca equals dCa over dt. Now, in order to perform the integral, we need to put the like terms together. Therefore, we need to take this term to this side and dt to that side. Okay. Which will look something like this. dt equals 1 plus K2 Ca over negative K1 Ca dCa. Okay. We'll integrate both sides, but before we do that, we'll plug in the values for K1 and K2. We might as well do that right now. So K2 is 3 per hour. 3 per hour, and K1 is 6 per hour. We'll leave this negative on the other side here. Actually, you know what? We'll use it to change the limits later on. So we'll integrate both sides. The integral of dt with limits from the initial time, which is 0, to the final time, and the integral of dCa has a limits of initial concentration to final concentration. Now we can use this negative here to switch the limits, which will look something like this. dt with limits from 0 to t equals integral of Ca to Ca naught, the initial concentration, 1 plus 3Ca over 6Ca dCa. Okay, Ca is 2 moles. Limits here will be 2. And the initial concentration is 8, which this will be 8 moles per liter. Okay. Now we can go ahead and integrate this equation, which will be something like this. T equals integral with limits from 2 to 8 of 1 over 6 Ca plus integral of 3 Ca over 6 Ca with limits from 2 to 8 dCa. Okay. We can go ahead and and simplify this equation further, which will look something like this. T equals, we'll take the constant term outside, 1 over 6 outside the integral, with limits from 2 to 8, 1 over CA dCA, plus these CA's will cancel. We'll be left with 3 over 6, which is 1 over 2, which can leave the integral because it's a constant, with limits from 2 to 8 dCA. That will give us T equals 1 over 6 ln CA, limits from 2 to 8, plus half CA, limits from 2 to 8. Okay, which will look something like this when we simplify it further. Ln 8 over 2 plus half 8 minus 2, which will give us a final answer of T equals 3.23 hours. So when we plot the concentration of A inside with respect to time inside the reactor, CA versus time, we'll know that the initial concentration started with 8 moles per liter of A, and it needed 3.23 hours in order to reach a final concentration of 2 moles per liter of A. And that is the final time required to reach a final concentration of 2 moles per liter. And the reason it's decreasing is because A is the reactant which is being consumed throughout the reaction to produce the product, which is B. The other hand, if you look at the plot of the concentration of B, which is the products, with respect to time inside the reactor, you'll notice that at time 0, the concentration of B was 0, and with time, you'll notice an increase in the production of B because more products are being produced with time. That's it for this video. See you on the next video, which will be on the theory behind the CSTR, the material balance of CSTR, and we'll do a couple of examples on that topic as well.